Let's now look at the Nernst equation. There are three key driving forces for a reaction: delta G, delta K, and E cell. All of those are telling you basically the same thing. It's a driving force for a reaction to proceed. Now, the first thing I want to do is look at the relationship between delta G and K. And that's given by the relationship that you see in green. And that is delta G under a set of circumstances is equal to delta G in the standard state plus essentially a correction factor. Now, if we then go assume that we're at equilibrium, delta G goes to 0 and the equation rearranges. Next thing we want to look at is a relationship between delta G and E cell. Delta G is equal to N, the number of moles, times Faraday, times the E, the potential for the cell. So you can see those two driving forces are related by that equation. Next, I want to look at the relationship between K and E cell, and that is the Nernst equation. The longer version you see is the equation there in green. The potential for any cell is equal to the potential for the cell in standard state, and then a correction factor term for non-equilibrium conditions. Notice that for E, you're going to see a Q, and at equilibrium, the equation reduces to the one you see there in red, but notice there is now a K there because you're at equilibrium conditions. And those are the three key equations. Now let's look to see if it can be simplified somewhat, because there are a bunch of constants in the number. So I've got the Nernst equation shown in the top right of this slide, and to the right of that I have a bunch of the numbers, the constants that we're going to use. For example, we know what R is, we know what temperature is at standard state, and we know what the conversion for a Faraday is. And so what that allows us to do is to greatly simplify the question, is to greatly simplify the equation. And a lot of those numbers just simplify down to that simple value there. Notice that there's a K there because this is the equation for equilibrium. Non-equilibrium conditions, that would be a Q. Now, there's also another version that you need to look at that's sometimes shown in textbooks, and that is where they use the log instead of the natural log, the log. And that's just a simple matter of correcting by the 2.303 value between natural log, and you have it. One thing you may want to do for a test is just to go ahead and rearrange that equations in different forms so you don't have to do the algebra during the test. And there's the full equation. Notice, again, there's Q because what? We have E cell. It's not in standard state. It's not at equilibrium. So we have a driving force, so we know that we're going to have a Q. So let's look at a sample problem here. Calculate K from tabulated EO values for the reactions of iodine and bromine. So what do we see? The first thing we're asked to calculate K, so we know we're at equilibrium, but we need to write a reaction for what is our equilibrium reaction. So we also know at equilibrium, not only is Q equal K, but delta G is 0. So we now can figure out which equation we're going to need to use. So as usual, let's do the analysis and we'll see what we know and what we don't know. So if we take the equations for delta G, which we know, delta G is equal to minus RT log K, but we know that delta G is also equal to minus NFE. So we can set those two equations together, essentially variations of the Nernst equation. And then what can we do? We could just plug them in, the values. We know R, we know T, we know N, we know F, and we know E. We know everything but one variable, K. It's just a simple matter of rearranging that so that K is on the left side of our equation and all of the variables that we know are on the right, and we plug them in and work that out. It's normally best to work it out leaving the log K there, work out all of the numbers, and then you can just get rid of the log term later on with the exponential function. And when you work through the calculation, K is equal to 2.7 times 10 to the 18th. Now what you really want to do is use the shortcut. That is, you don't want to plug all of those numbers in. Use that shortened equation that I gave you earlier, and you can see the math is much, much quicker and simpler. And the simpler the math, the less likely you're going to get it wrong on a test. Let's look at a second problem. Calculate E cell for iron 3 to iron 2 electrode when the iron 2 is exactly 5 times that of Fe3. So let's think about that. Let's analyze that. What do we know? Well, we know we have a half cell, and we could look up the standard potential for that. And we know something about the concentrations of our products and our reactants. And if we know that, we can calculate Q. So at the end of the day, we're just relating EO to K, and that's the Nernst equation. I would highly recommend you use it in a simplified form when you can. Notice that because we're not at equilibrium, that we do have a Q value instead of a K value. Our half cell reaction, it tells us Fe3 plus goes to Fe2. We can look up the standard state potential for that half cell reaction. It's 0.771 volts. So let's take inventory. We now know the standard potential for the cell. We know our constants. We know what N is from writing out that half cell reaction. And even though we do not know the concentration of our reactants and products, we do know the ratio. And that's what we need to know. At this point, we have one equation, one unknown. It's simply a matter of filling in the values, getting the correct ratio for your products over reactants, and solving the equation algebraically. The answer, 0.730 volts. And there the answer is written out in more of a script form where I highlight some of the thought processes. And that's it for this section of the Nernst equation.